Moving on to some more first stats 1 revision here, we're going to look today at probability generating functions. So this is the penultimate chapter of the official Edexcel Further Stats 1 textbook. So we've got mixed questions here. Now this wasn't on any of the previous further maths specifications, so there are going to be no exam questions, but everything's taken from this textbook. So be sure to follow along if you want to work through. But if not, we'll go through it together here. So the question, the first question here is from exercise 7a, question 8. And we've got this probability generating function of a discrete random variable x. So part H wants us to find the value of k. So let's get a pen up, use white. So question AA. Well, this is a pretty standard question. It's something you should hopefully be aware of, that if we use the fact that using t is equal to 1 here, so I'm using the probability generating function of t being equal to 1 like this. Well, when I sub t into 1, t equals 1 into this function here, the full function should be equal to 1. So using this fact here, that this is equal to 1, well, that would be k lots of 1 plus 2 times 1, so 2, plus 2 lots of 1 squared, so that's going to be 2 times 1, so that'll be another 2 there. And we square all that, that's going to be equal to 1, okay? So k times 1 plus 2 is 3, plus another 2 is 5, square that, so that'll be 25 is equal to 1. So therefore 25k is equal to 1, so k must be 1 over 25. Okay, so a nice little easy opener there, just finding the value of k. Now part B, a little bit tricky but nothing too tricky. We've just got to write down the probability distribution of x. So because this is a discrete random variable, if we had to expand this right hand side here, so expand the right hand side using k equals 1 over 25, what that will do is it will give us the coefficients of t to the x, and then them coefficients match to our distribution. So let's just start by expanding and then we'll elaborate on that point. So if I expand this, so this is k, so 1 over 25 times 1 plus 2t plus 2t squared times 1 plus 2t plus 2t squared. Okay, so we need to multiply these two brackets out. So I'll have a 1 over 25 on the outside. What I'm going to do now is just put everything in one bracket here. So I'm going to multiply everything across. So 1 times 1, I'm going to do 1 times 2t and then 1 times 2t squared. And then move across, so I'm going to do 2t times 1, 2t times 2t and so on. So let's start doing that. So 1 times 1, 1 times 2t, so that's just 2t. And then finally 1 times 2t squared, which gives me a 2t squared. Next 2t times 1, that'll give me another 2t. 2t times 2t, so that's 4t squared. So just be very, very careful here now with your powers. And then 2t times 2t squared, so I'm going to get 4t cubed. And then finally 2t squared times 1, so that's going to be 2t squared. 2t squared times 2t, so that'll be 4t cubed. And then finally 2t squared, so that'll be 2t squared times 2t squared. So that will be 4t to the 4, okay? So that's the full expression here, but obviously we need to start simplifying this. So this will be 1 over 25. So if we simplify everything here, well, we've only got one constant here, that's just the 1. I've got a 2t, another 2t, and I think that's it. So yes, that'll just be 4t. I've got a 2t squared and a 4t squared, and then another 2t squared. So there's a lot of t's and squares going on here. So that's 4t squared plus another 4, so that's 8t squared. And how many t cubes we've got? A 4t cubed and another 4t cubed, so that's 8t cubed. And then finally, just got the 4t to the 4 at the end. Okay. So that's my full expression here once we've expanded it. So now, using the coefficient of t to the x. So what I mean by that is, so for example, if the 8t squared here was, say, let's just say 6t squared, okay, because that's the 2 there for the x, what that means is that the probability that x is equal to 2 would be, it would be 6 out of however many t's we've got here in total. So in this case, we'd have 25 lots, right? So that would be 6 out of 25. If I was using it for this example, but because ours is 8, it'll be 8 out of 25. So let's start setting that up for ours. So I'll just rewrite this bit at the top, just so we've got enough room here. We can finish it off up here. Get rid of all this. Can't quite eliminate all the rest of it. There we go, that should do. So all we've got to do now is set up our table. So I've got a 1, a 4t, an 8t squared, an 8t cubed, and a 4t to the 4. So what that will be is we'll have our x, we'll have the probability, that big X is equal to this x. So because that's just a 1, and there's no t with it, that'll just be 0. The 4t, that's t to the 1 here, so that'll just be x equals 1. My next one, the t squared, will be 2, and so on and so on. So that'll be 3, and finally we'll have the 4. Okay, so that's all we'll have across the x row here. So now, because it's 1, just 1 here, there's no t with it, that'll just be 1 out of 25. I've got 1 here, so that matches with my t, so that'll just be 4 out of 25. Same again here now, so this is 8 t squared, so this is the one we were talking about before, so because it's 8, it'll be 8 out of 25. Same again, it's 8t cubed, 8 out of 25. And then finally the last one has to be 4 out of 25. A good way to check your answer is that these should add up to 25 over 25, the sum of it. If you do that, what you will find is that it does come to 25 over 25. So there we have it. So that's all we've got to do for the probability distribution of x. Okay, so that's 5 marks in total for that question. Hopefully nothing too tricky. I think the key bit with that question is just remembering the fact that the coefficient here of t to the x matches for the probability. Okay, so that's that question. Let's jump into the next one. So the next one is from exercise 7b, question 7. And it's a question here that's looking at showing from first principles the probability generating function for x, which is defined as this here. So this g x of t is equal to e to the 3.5 bracket t minus 1. So 5 marks for this. So the first thing to try and figure out is what distribution this is. Now, you might be aware of what distribution it is from the probability generating function. If you've done enough practice with these kind of questions, you'll recognise it straight away. But if not, read the question and see what it's telling you. So we've got calls coming in to a call centre at a rate of 3.5 calls per 5-minute interval. So that's the key bit, that we're looking at a time frame. So it's an interval of time. So because it's an interval of time, straight away it's got to be Poisson distribution. So if we write that down, that'll be x distributed with a Poisson distribution. And my mean is 3.5 calls per 5 minutes. So that has to be 3.5 like that. Okay, that's the mean. So remember how we define a probability for a Poisson distribution. So the probability x equals x. Well, that's going to be, so using this Poisson distribution here, so that'll be e to the minus 3.5 times 3.5 to the x all over x factorial. Okay. Now the probability generating function can be defined as follows. So the probability generating function for this function here, x for this discrete random variable, or just a random variable, sorry. Well, that can be defined as the sum of t to the x times the probability here. But we've already defined this, right? Okay, so the probability of x being equal to x, that's what we've got. So all we've got to do is substitute this in now. So that will just be defined as the sum of t to the x times e to the minus 3.5 times 3.5 to the x all over x factorial. Okay, now we're going to have to do a bit of manipulation here. And what I'm going to do first, I'm going to pull this e to the minus 3.5 in front of the summation. Okay, so just like you should be aware of this when you've done it with core pure, we can pull out in front of the summation. So what that will be is, if I do it over here, so that'll be e to the minus 3.5 times the summation. And the reason why I'm pulling this out is so I can move this t to the x with this 3.5 to the x here. Okay, and we're going to get it all in terms of 1 power. So that'll be t to the x times 3.5 to the x all over x factorial. So now what we can do is write this as just one product here, and in terms of one power, so that would be e to the minus 3.5 times the summation here of 3.5 t to the x like that. Okay, that's all over x factorial. Now this is important, so to give you an idea of what you've got and what you're dealing with, I'd do a couple of terms just so you can see what you're working with. So what this would be now, if we do it over here just so we can see it fully, so I'll always have an e to minus 3.5 on the outside. So let's start working out a few terms now. So put t is equal to 0 into this will just be 1. So my first term will be 1. Put t is equal to 1 into here, so that'll be 3.5t to the power 1, so that's 3.5 divided by 1. Okay, so that'll just be 3.5t. Keep going with this now, so this would be 3.5t squared divided by 2 factorial. Okay, so just keep going so you can see what you're working with. I'll do one more term just to fully make it clear. Sorry, that'll be 3 factorial. Yeah, I'll try it as 3 factorial. So that'll be 3 factorial. That'll be 2 factorial there. Okay. Now obviously this summation will keep going. But you've got to recognise what this actually is here. So this full expression here, this is actually the Maclaurin expansion of e to the x. So this is the Maclaurin expansion of e to the x, where x is equal to 3.5t. Okay, so using that fact now, we can just change this. Okay, so if I just eliminate some of this up here just so we've got enough room to finish it. Get rid of all this. Okay, we can finish it up here. In fact, I'll just go to this as well. Okay, so we can finish this off now. This will just be now the probability generating function. Oh, sorry, that'll be a g. T. So this is equal now to my e to the minus 3.5 multiplied by e to the 3.5t multiplied by e to the 3.5t. Okay, because that's what this Maclaurin expansion is here. It's e to the x where x is 3.5t. So we're just multiplying it by that. Okay, so we've got this now. Well, this is just a product now of indices, so using your indices rules here, I can write this as e to the 3.5t minus 3.5. Okay? And now we can just take this one step further by factorising out the 3.5, so this will be e to the 3.5 bracket t minus 1. Okay? And that's exactly as what we've got to show it as. Okay, so they've shown it here, and we've got it here. So this is as required. Okay, so 5 marks for that. You know, it's just got to be careful with your manipulation and that, and then just recognising here that this is the Maclaurin expansion of e to the x, where x is 3.5t. Okay, so I hope that's clear. What we'll do is we'll jump into the next one. So this one's from exercise 7c here. Now this one's looking at showing, or partly what the main idea of this question is, showing the mean and standard deviation for a probability generating function. So let's have a go at part A. So question 11, part A. So it just wants us to state the distribution of x, the number of calls received in a single 15-minute period. So let's just read the question. So we've got a call centre again receiving incoming calls at an average rate of 4 per 15-minute period. So because we're looking at a time frame again, you know, over a certain time frame, it's got to be Poisson again. So x, it's a Poisson distribution, and what's my mean? 4 per 15-minute period. So I'll just go write that as a mean of 4. Okay, and that's simply all you've got to do for part A. So don't overcomplicate it, it's just simply what it is there. The probability generating function of x. So this now is what we just did previously with the last one. So this would be e. So if I write it in full, it'd be g, t, for the probability generating function of x. This will be now e again to the lambda, so that's 4 bracket t minus 1. Okay, so that's simply all it is. You've just got to replace the lambda here with what your lambda is. So because our lambda is 4, we replace it with 4. And that's simply all it is. Now for part C, we've got to use the answer to part B to show that the mean of x is 4 and that the standard deviation of x is 2. Okay, so 7 marks in total for this. Now sometimes these will be nicer than others. This one's nice because it's a Poisson, but because it's in terms of E here, and this is what happens when you've got it in terms of Poisson. So you'll see why it becomes quite a nice question in a second. So let's just start out by defining what the mean is. So the mean is when we differentiate this probability generating function. So g prime of this function for x here. Well, if I differentiate this here, so differentiate e to the 4 bracket t minus 1, well that'd be 4t minus 4, so the derivative of that would be 4, bring that to the front here, so that'd be 4e to the 4t minus 1. Okay, so just a standard differentiation there from your A-level maths. But we define the expectation, so the mean of x, so e of x, as being the derivative at 1. Okay, so if I sub 1 into this function now, what will I get? So that'll be 4e to the bracket, to the power of 4, 1 minus 1. Okay, so that'll be 4e to the 4 times 0, so that'll be 0, and then e to the 0 is 1, so that's 4 times 1, just giving me 4. And that is all we've got to do for that. Okay, so this is quite a generous question, and if you got this on your exam, I'd be very, very happy, because it's quite a nice question. So simply 4 as required. Part B, or part 2 of this part C here, we have to show that the standard deviation of x is 2. So that was part 1. So the standard deviation of x, well, we define that. Well, first we define the variance of x. So the variance of x will be equal to the second derivative of g, but we define it at 1. So if I just write that as 1 plus the first derivative at 1 minus the first derivative squared. Okay, now we've already got the first derivative at 1, that's 4, so that's going to be nice and easy, but we need to work out the second derivative. So differentiate this once more, so just do it over here, g prime prime, what will that be? So that'll be basically just going to bring another 4 down here times 4 by 4, so that'll be 16e to the 4 t minus 1. Okay, but we need to do this at 1 now, so as you can just see what's going to happen here again, this will be 16e to 0, so that'll be 16, so that's going to be 16 plus 4 minus 4 squared. Okay, so that's going to be 20 minus 4 squared, which is 16, so 20 minus 16, which is equal to 4. But we want the standard deviation, we've got the variance, so to get the standard deviation we just need to square root it. So using the fact that standard deviation is equal to the square root of the variance of x, which is going to be equal to the square root of 4, which we simply know is 2. Okay, so 4 marks for that. Quite a nice one, and it's nice and easy because you've got it in terms of e here, and obviously it's much nicer to differentiate this e expression here. Sometimes you might get this as a nasty quotient, and you've got to start using product rule and quotient rule, and it can get quite nasty, whereas with it being in terms of e, it's very nice to differentiate. So okay, so that's all we've got to show for that one there, and that'll get you all the marks given for that question. We've got exercise 7b here, question 4. So a dead brief one, I'm just kind of throwing it in, there's a bit more practice. So we've got a sailmaker notices that the flaws in a roll of sailcloth occur at an average rate of 0.3 per metre. So part A, we've got to suggest a suitable model for the random variable x. So just like we did with the last one, we've got to define the function and what the, basically what the, what's the word I'm looking for? What the distribution is. Okay, so I couldn't think of the word there. So what the distribution is, so if we read it, so we've got a sailmaker making the rolls of sailcloth. So because it's happening again at a rate of something per, so it doesn't always have to be time. I know I normally say time, but it could be like per metre here. It's got to be Poisson again. So x EX for the random variable x, so x a Poisson distribution, and my mean is 0.3, an average rate of 0.3. Okay, so that's just simply part A. Part B wants us to find the probability that x is equal to 1. Okay, so don't overcomplicate this. You want to work out the probability that x is equal to 1 using this Poisson distribution. Okay, so you can just put this on your calculator, or you can use the formula. Seeing as I'm doing it by hand anyway, I'll just use the formula, but I would just use your graphical calculator if you can use the Poisson function for it. So this would be e, so minus 0.3 times 0.3 to the 1 all over 1 factorial. Okay, put all that in your calculator, and what you'll get is 0.222. Okay, so it's just simply 1 mark. And then finally, part C, we just have to write down the probability generating function for x. So just more practice, remember. So we'll write out in full for x being a Poisson distribution with a mean of lambda. We can define the probability generating function here as being e to the lambda t minus 1. Okay, so e to the lambda, that's a really bad lambda symbol, times t minus 1. So in our case, we know our lambda is 0.3, so therefore our probability generating function is just going to be simply e to 0.3 times t minus 1. Okay, and that's all you've got to do. It's as easy as that. And then moving on to the very final question here, I've got it incorrect. Okay, so I can finally finish this now. I'd actually done the question, put it down, but I hadn't actually put the actual picture of it on, so you won't have had much to work from currently from that. So we can finish this off now. Question 3, this is from exercise 7D. So this is looking at the combining two probability generating functions here. So part A, we just got right down the probability generating functions for x and y. So they're both Poisson distributions, so we've worked with quite a lot of Poisson distributions in this video. And simply, just like we've been doing before, just got right down the probability generating function. So the first one will do x, so that will be e to the mean, which is 1.3 times t minus 1. Okay, let's do y now. This is dead quick once you've done a couple of these. This will be e to the mean again, so what's my mean? 2.4 bracket t minus 1. So that's literally all we've got to do for that one. So there are two probability generating functions. Now part B, for 1 mark, just asks us to write down the probability generating function for z equals x plus y. So for this, using independence, so we're using independence, and we're told that they are independent, so using independence, what we can do is write this as a product. So the probability generating function of z can be written as the probability generating function of x and the probability generating function of y. So if we write that down, that'll be g probability generating function for x times the probability generating function for y. Okay, so what that'll be, if we write that down in full, that'll be e to the 1.3 bracket t minus 1 times e to the 2.4 t minus 1. Now don't be put off here by the powers. Imagine you used to expand both of these powers, so that'd be 1.3t minus 1.3, and that'd be 2.4t minus 2.4. So if you had 1.3t, now because we're times these, we add the powers, so 1.3t plus 2.4t, that'd be 3.7. That'd be e to 3.7, so right on the outside. And if you were to do the same here with the minuses, minus 1.3 minus, or add minus 2.4, it'd be the same as just subtracting it. You're going to get minus 3.7. So we can write that as a 3.7 on the outside and t minus 1 on the inside of the bracket like that. Okay, and that's all you've got to do just for 1 mark. So it's just multiplying the two probability generating functions to give me probability generating function for z. And part C just wants us to use the answers to part A and B to show that the expectation of z is equal to the expectation of x plus the expectation of y. So what I'd do for this is work out the expectation for z first, work out the two expectations of x and y separately, add them together and just show that they are equal. So if we do this over here, so part C, let's do z first. So g prime z, so that'd be differentiating this here. So again, because it's a Poisson, really easy, just times it down. So that'd be 3.7 e to 3.7 t minus 1. But remember, the mean now comes from, we sub 1 into here, so E of Z. So that'd be 3.7e to the 0 basically, so that'd just give me 3.7. Okay. Now let's work out the expectation of x and the expectation of y. So we need to differentiate g of x, or the probability generating function of x here, and the probability generating function of y. So e of x, well, that'll be g prime here of x when we sub in 1. So the multiply down here, so that'd be 1.3 e to the 0, so that'd be 1.3 e to the 0, which would be 1.3. Do the same with e of y. So that'd be the generating probability generating function here. If you differentiate it, sub in 1, that's what we'll get for the mean. So that will be 2.4e to 2.4 bracket t minus 1. So imagine you sub t's 1 into that, that'll become 0. So you're going to get 2.4 e to the 0. That'll just give you 2.4. So if you add 2.4 to 1.3, what do you get? We get 3.7, so perfect. So therefore, 1.3 plus 2.4 equal to 3.7. So therefore, e of z is equal to e of x plus e of y. And there we have it. So 4 marks for that. Again, quite a nice one, I'd say, overall. But there we have it. So that's the end of this video. I hope this has been helpful. So this is probability generating function. So this is pretty much towards the end of the further stats one. If it's helped, be sure to subscribe, leave a like, any feedback down below. I'd really appreciate that.